तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last class we had we were discussing CMOS static RAM, and we had also introduced the concept of BiCMOS static RAM, and today we shall continue our same discussion. We had seen that if you take the block diagram of a memory of a static RAM, when we of a CMOS static RAM, when we convert it to BiCMOS static RAM, some of the elements are we retain the CMOS. For example, in the memory cell array, because of the fact that the CMOS is a more dense circuit, that is it requires less area, as at the same time the power dissipation is less. So, we would retain the CMOS for the memory cell array. The decoder drivers are BiCMOS because they are BiCMOS is capable of driving very large capacitive loads, and we have a very large capacitive loads. The word lines and the data lines are very large represent very large capacitive loads. Then the sense amplifier, on the other hand, is bipolar, completely bipolar, in the sense that because of the fact that the bipolar transistor has a very large transconductance and is able to sense very small voltage differences along between the data and data bar lines. Now, the buffers here are bipolar, is shown as bipolar because many of these BiCMOS memories have ECL type of inputs, which means that the levels are the same as the voltage levels are the same as that for an ECL, that is, you have negative voltages as in an ECL. This must be converted to the levels which are understood by a CMOS circuit, because the memory cell is basically CMOS. So, what is done is we retain it, the negative voltages are retained, but it is converted to CMOS levels, which we shall see today's class. And the control circuit is also BiCMOS, in the sense it contains both bipolar and CMOS components. And the output buffer, because again it is an ECL type of IO interface, so the output buffer is bipolar because the output is an ECL type of levels, voltage levels. So, with this type of modification, the CMOS memory can be converted to a BiCMOS memory, and this gives rise to a lot of improvements in power, in especially the speed or the reduction in the access time in the memory, that is, the delays are very much reduced. Here we show a comparison of the delays of a CMOS and BiCMOS memory. This is in fact, I will just also give the reference. The reference is M. Kubo et al. The name of the paper is Perspective on BiCMOS VLSI, IEEE Journal of Solid State Circuits, volume 23, number 1, page 5 to 11, February 1988. So, in that paper, what they do is they make a comparison of the delays of the various elements in a memory. They compare the delays of a CMOS memory with that of a BiCMOS memory. Okay. The delays can be broken up into different the delays through the various regions of the memory. For example, first you have the input buffer. So, the delay corresponding to an input buffer, then you have to decode whatever address has been floated. So, that address has to be decoded. So, there is a delay for the decoder. Then the output of the decoder must be driven through the memory array, that is you require a data driver. Okay, for example, the word line, the entire word line represents a large capacitance, so that the entire you require a driver to change the word line voltages. Okay. So, there is a large delay involved in that, and then once you select a particular cell, the contents of that memory cell must be sensed by the sense amplifier. So, first is you select a memory through the decoder, select a particular cell, then that by driving the word line, and then you use there is a sense amplifier to sense the contents of the memory, and then the output of that sense amplifier must go to an output buffer. There is a delay component for that. So, these are the different delay components in the memory. So, what they have done is they have analyzed the total delay and broken up into different components. So, for example, if you take a CMOS memory, they have taken a CMOS memory. So, this is for a 2 micron technology. So, it is a rather old technology, but at the same time it gives a very good comparison. Okay. Now, they do not specify the size of the memory in their paper, but anyway, let us see. The delays are for a CMOS 4.8 nanosecond at the input buffer, 8 nanosecond for the decoder, and the major part of the delay is for the memory cell data driver and sense amplifier, total of 13.4 nanoseconds, and finally the output buffer 2.3 nanoseconds. If you now compare for a BiCMOS, we find that the input buffer, the delay is reduced from 4.8 nanoseconds to 2.8 nanoseconds, the decoder from 8 nanoseconds to 6.5 nanoseconds, but the major reduction is in the delay for the data driver and sense amplifier. The data driver is now a BiCMOS driver, okay, and the sense amplifier is a bipolar sense amplifier. So, here the 13.4 nanoseconds for a CMOS is reduced to 4.4 nanoseconds only. 4.4 only. So, there is a major reduction here, and the output buffer, of course, this 2.3 nanosecond has slightly increased to 2.5 nanoseconds, because again the voltage in the case of a BiCMOS, again what happens is you have to convert the CMOS levels to ECL levels. So, there is a slightly larger delay, but if we compare the total delays for the CMOS, while it is 28.5 nanoseconds, it has gone down to 16.2 nanoseconds for a BiCMOS. So, you see that there is a large reduction in delay if we convert a CMOS, if we take a BiCMOS static RAM. Okay, if you convert a CMOS static RAM into a BiCMOS static RAM by making the necessary changes, that is by introducing bipolar transistors at judiciously, okay, and in different regions. Okay. So, what we shall do in today's class is we shall take up the different components in a BiCMOS memory and see what are the changes that has to be take place, okay, or the changes that we must make in the static CMOS static RAM in order to improve the performance. Firstly, let us take the memory cell array. Okay. In the memory cell array, we have said that this is going to be a CMOS, okay, just like as in a CMOS static RAM, but there is a small difference in BiCMOS static RAMs. The cell which is used is slightly different from a CMOS static RAM cell. Instead of the normal 6 transistor cell which is used in CMOS static RAM, we have a 4 transistor cell. Okay, it is like this. So, this is the cell which is used. So, this is the word line, this is the data lines. Okay. So, what we have is, what we see is that the inverter here is not the conventional CMOS inverter, that is, it does not have a PMOS load, but it has a resistive load. Okay. In this, okay, so you basically have two inverters back to back, as in the case of a CMOS cell, 6 transistor cell, but what we have is a resistance load. Now, this resistance is made of polysilicon, and polysilicon, if it is can be undoped polysilicon, can have very large resistances. In fact, these resistances have are of values as large as 10 gigaohms. Okay, so these are very large resistances. Now, so if these resistances are very large, the current which flows when okay, is going to be extremely small. So, if you have 10 gigaohm resistance, so the currents will be less than nanoamperes. So, in fact, so even if you have an inverter like this, the power dissipation is not going to be high. Now, the problem with this type of cell would be that since this resistance is very large, the current when the current flows through this resistance, the current is going to be extremely small. So, if this data line has to be charged to high, since the current would be very small, it would take an extremely large time. So, these resistances cannot be depended upon to pull up the data line voltages. So, what can be done is, so if you have a particular configuration, this is on, this is off, obviously then this is off means this is logic 0, and this is off means this is logic 1. Okay, so this is the inverter, so this output of this inverter is 0, so this goes here, so this is off, which means that this is 1. And this is on, this is on. So, if this is the condition, okay, then if this particular cell is selected, since this transistor is on, this is going to help to discharge this line voltage, but this cannot be depended upon to pull up the line voltage that side. So, what is done in this case is that the data lines are pre-charged to VDD, that is the supply voltage, that is the highest voltage in the circuit. So, one of these lines is going to be pulled to a slightly lower value because of this on transistor. Okay, this is connected to an on transistor. So, this voltage is going to go down by a small amount, and this has to be sensed by the sense amplifier. So, the pre-charge voltage in this case is going to be VDD, or the highest voltage in the circuit, and then in which case, so it is one line is going to be pulled down, the other line is not going to be pulled up. So, you do not depend upon this resistance in fact to pull up. Okay. Now, what is the advantage of having a cell like this, okay, 4 transistor cell? Of course, what we do is we avoid the use of PMOS transistors, and you know that in a CMOS, if you have NMOS and PMOS, they in order to fabricate them, you have to have some 2 tubs, okay, in which one you fabricate the NMOS and the other one the PMOS is fabricated. So, that takes up area. In fact, these resistances, these large resistances, these are polysilicon resistances, these are folded on top of the NMOS transistors. Okay, these are fabricated on top of the NMOS transistor. So, you have the NMOS transistor, and on top of that, so you have insulator in between, and on top of that you have the polysilicon resistances. So, these polysilicon resistance in fact do not take up any extra area, they are on top of these NMOS themselves. So, in fact, the area requirement for this cell is almost half that of the CMOS cell. So, there is a tremendous reduction in area, which is the advantage of having this 4 transistor cell. The other thing is that you do not have extra power dissipation because of these very large resistances, the currents are very small. At the same time, the disadvantage one would expect is that because of these very large resistances, it cannot pull up the voltages. Okay, they cannot be depended upon to pull up the output voltages, but since that is taken care of by pre-charging the data lines to VDD, so there is no need to pull up, only the pull down is done by one of the transistors, on transistor, and because of that differential voltage is created, which has to be sensed by the sense amplifier. So, this is about the memory cell. We shall now take up this part, the decoder driver part, and see what are the changes, what are the circuitry which is used in BiCMOS static RAMs, and basically the modifications with respect to a CMOS static RAM. So, now let us look at the BiCMOS, the circuits used in BiCMOS static RAMs, the input side. Okay. Now, as we said that the inputs are basically ECL inputs. So, in that case the logic high would be say minus 0.9 volts and the logic low would be minus 1.7 volts. So, what is done is these are the what are called ECL receivers. So, now what we have is a differential a stage ECL type of stage here. So, depending on and you have a reference voltage here. So, depending on whether this voltage is high or low, one of these two transistors is going to conduct, and so there is a current going to flow through these resistances. So, the voltage levels on these two lines is going to be different, and then what you have is the next stage, which is called the level shifting stage, okay, which basically converts these ECL levels to the levels which are understood by this circuit, which is nothing but a BiCMOS inverter. Okay. This is the standard BiCMOS inverter circuit that we have already seen. Okay. So, this is doing a level shifting. Now, let us see how this is done. Now, depending on the voltages here and this reference voltage is chosen properly, then the current, okay, flows in either of these two branches. So, suppose one voltage is going to be output voltage, let us call is V high, and the other one is V low. Okay. So, at the two collectors. So, if V high, that is the high voltage, okay, is when there is no current flowing through this resistance here. Okay. So, what is the output voltage here? V high, it is, this is ground and this is minus VEE, as in the case of in ECL. So, this is minus 5.2 volts, which is the standard voltage for ECL, and this side is at ground. Okay. So, now you have a diode drop here. So, there is no current flowing here. So, V high can be said to be is equal to minus VBE, which is the diode drop. Okay. And V low will be minus VBE minus IE RC, okay, where RC is this resistance value. Okay. IE is actually this the value of this current source here. All right. So, IE, the entire current flows through this resistance. So, the drop here is IE RC. All right. So, this is now fed at the gate of this PMOS transistor. All right. So, this PMOS transistor, one PMOS transistor has a gate to source voltage of minus VBE, and the other PMOS transistor has a gate to source voltage of minus VBE minus IERC. Now, if the threshold voltage of the PMOS transistor lies between, okay, if the threshold voltage, the modulus of that lies between VBE and VBE plus IERC, okay, then what is going to happen? One of these PMOS transistors is going to be on, that is conducting, and the other one is going to be off. All right. So, one branch again in this level shifting, one is going to conduct and the other one is going to be off. Now, this circuit, if you look at it closely, this consists of these two NMOS transistors here is in a current mirror type of configuration. Okay. So, that because both gate voltages of these two transistors are the same, and this also the sources are also at the same potential. Now, if we consider this current here which flowing out of this level shifting stage as I load, this is I load is can be written as I P2, that is this transistor, this is this current minus this current which we call the current mirror, okay, ICM current mirror, okay, that is the I load, okay, that is the current flowing here. Now, this ICM is ICM because of this current mirror configuration. Okay, this is nothing but the same as IP1, okay, because this current is the same as this, okay, and the current flowing through this NMOS transistor here is the same as the current flowing through this PMOS transistor P1. So, you can write I load is equal to IP2 minus IP1. So, there is a current flowing out here, this is the charging current for the input capacitance of the BiCMOS inverter. Okay. So, this current is actually the difference of IP2 and IP1, IP2 minus IP1. Now, as we have already said, there can be two possible cases, that is either P1 on and P2 off, or P1 off and P2 on, all right. So, in one case, if P2 is on and P2 is on and P1 is off, so this I load is going to be positive, and in the other case if P1 is on and P2 is off, I load is going to be negative. So, if I load is positive, that basically a current flows into the input of this BiCMOS inverter, it charges the input capacitance. So, that basically is a logic high at the input, so the output is going to be low. On the other hand, if the I load is negative, that is basically discharging the input capacitance of the BiCMOS inverter, okay, then what happens is this input is construed as a logic low, which means that the output is going to be taken as a logic high. So, depending on the input right at the here, okay, depending on whether this input is high or low, one of these two branches current is going to flow in one of these two branches. So, it makes one side high and the other side low. So, again depending on the input, one side will be high and one side will be low. Depending on that, either P1 will be on or P2 will be on, the other transistor will be off, and depending on that the load current is either going to flow into the input, I mean there is going to be a current flowing out which is charging or discharging the input. So, depending on that the output is going to be high or low. The important point here is that the input here is the ECL level, okay, whereas here see the current flowing in here, it charges the input capacitance here. So, this is a BiCMOS inverter, all right. So, the output level which you get here is minus, as in the case of BiCMOS. So, you will get there is a VBE drop from the logics, this is minus 5.2 here and 0 here. So, you get minus 0.6 and minus 4.6. So, high will be minus 0.6, low will be minus 4.6. So, basically we convert the ECL level to BiCMOS level. So, this is basically CMOS level, okay, except that it has been level shifted down to negative values. Now, once this is done, then you can use normal BiCMOS circuits to do the decoding operation, okay. The decoding operation can be done by using normal BiCMOS circuits, okay. So, this is one way in the BiCMOS BiCMOS static RAM which uses ECL levels, that is you first convert it to BiCMOS levels, okay, and then follow it up with BiCMOS circuitry to do the all the logic operation needed for decoding as well as for driving the through the word line capacitances. We use BiCMOS drivers, okay. So, this is one way which people have employed, okay, to in BiCMOS static RAMs. Another way I shall now talk, another decoding mechanism is uses a different concept. See here again the inputs are in ECL level, okay. So, what is done is first we have a say a ECL OR NOR circuit. You know that ECL gates you can have outputs of you can have the same output as well as the complement. So, basically this is a NOT and that is you get at the output A naught as well as A naught bar, okay, and you know that this is the basically the emitter follower which is at the output of the ECL inverter. So, these are basically ECL gates here, okay. So, you have ECL gates and this is the emitter follower at the output of the ECL gates. Now, we know that the output of the ECL gates, because you have emitter followers, you can do a wired operation, okay. So, you can get logic, okay, by doing the wired operation. For example, here what you have is this is A naught bar. So, we are just have drawn a circuit which takes the two inputs, okay, two input decoder. So, basically you will have 4 outputs, okay, 2 by 4 decoder. So, you have this is A naught bar and this is A naught, okay. sorry, this is these are both A naught bars, sorry, these are both A naught bars, okay, and here you have A naught and A naught. Okay, so this is the emitter followers, this is multi emitter transistor at the output of ECL, whereas here you have A1, A1, A1 bar, A1 bar, A1 and A1. Now what you do is, at this, if you take this line, okay, so A naught bar and A1 bar is connected here. Okay, so this is nothing but an OR of A1 bar and A naught bar. Okay, then here in this line you connect A naught bar and A1. So this is an OR of A naught bar and A1. So in this line you have A naught or A1 bar. So here you have A naught or A1. So basically you have all the 4 combinations. Okay, so just by doing a wired operation you do the decoding. Okay, so you have a 2 to 4 decoder. This decoding is done at the ECL level only. Okay, it can be done very simply because the ECL you can do a wired operation. So this decoder can be realized very simply by doing a wired operation. Okay, here you have the current sources, of course, going to ground. So this is a wired operation, okay, and then what you do is you do the same thing as you have done in the previous case. Each of these outputs of the decoders are level shifted and using a BiCMOS driver you drive the memory word lines. So the difference here is that the difference in the 2 circuits is, in one case what you do is you convert the ECL levels to BiCMOS level and then you do the decoding at the BiCMOS levels. Okay, so the voltage levels of the decoder is the BiCMOS level. So you do the decoding using BiCMOS gates. Okay. On the other hand, what you can do is at the ECL level itself, using the property of ECL that you can do a wired operation. Okay, you do the decoding itself. So you have a 2 to 4 decoder. You have 4 outputs here. Okay, you have 2 inputs. You have 4 outputs now, and then each of these 4 outputs, okay, you have to do a level shifting and then a driver to drive it through the memory cell array. Okay. So these are the different types of circuits which are used at the input of the static RAM, BiCMOS static RAM. So the important point here is that although at the input you have ECL levels, at the output of the driver you have CMOS, basically CMOS levels, okay, except that it is negative, voltages are driven negative. So it is level shifted down. Okay, there is a level shift to negative values, but the voltage levels are still the same as in a CMOS. So you have a complete 5 volt, almost a 5 volt. Okay, if you are operating 5 volts, 3.3 volts. If you are operating, you will have a 3.3 volt, almost a 3.3 volt difference between the high and low logic levels. So you can use all the voltage levels shifted down to negative values by the same amount. So you can get basically the same CMOS operation, but again one must remember that one must again revert back to ECL levels at the output stage. So next what we shall do is we shall look at a complete circuit, okay, or basically not the so this is the input circuit, then the remainder of the circuit we shall look at a circuit for a static RAM and look at how one can read and write okay, in a BiCMOS static RAM. So now let us take up for discussion particular circuit for a BiCMOS static RAM. Different groups have people or companies, they have different circuits for BiCMOS static RAM. I have just taken one representative circuit which is from literature, and let us just discuss this particular circuit and see how the circuit actually functions. So this circuit which I am going to discuss now is actually taken from this particular paper, R.A. Curtis et al. Okay, 12 nanosecond ECL I/O 256K into 1 bit SRAM using a 1 micron BiCMOS technology. It is from IEEE Journal of Solid State Circuits, volume 23, page 1048 to 1053, October 1988. So, this is just one of the representative circuits, and we shall just go through it, how the reading, writing and different operations are taking place in a particular BiCMOS static RAM. Now, as we have seen, this is a 256K into 1 bit static RAM. So, 256K static RAM means that there will be 256K cells. 256K is actually 2 to the power 18. So, there will be 2 to the power 18 cells, okay, and one has to select 2 to the power 18, 1 out of 2 to the power 18 cells. So, if you have 2 to the power 18 cells, there will be 18 address inputs, and one has to, with the help of these 18 address inputs, one has to select a particular cell. So, let us look at how this is done. So, what is done is you have columns, again just as in any memory cell, you have columns in which you have the cells. So, there are actually in each column there are 128 cells, x0 to x127 here. So, each column will have 128 cells. So, if you have 128 is 2 to the power 7. So, if you have 2 to the power 7 cells per column, so this is again the 4 transistor 2 resistance cell which we have already discussed. If you have 2 to the power 7 cells, so there must be 2 to the power 11 columns. So, what is done, you have a particular decoder, okay, which is a 7 to 128 decoder, which selects one cell in each of these columns. Okay. Now, to select one of the 2 to the power 11 columns, what is done, you have another 2 decoders, not one decoder, but 2 decoders. What is done is this 2 to the power 11 columns is now divided into groups. Okay. So, each group consisting of 16 columns. Okay. So, what is done is, so each of the 16 columns, that is 2 to the power 4 columns constitute a group. Okay. So, you have another decoder which is a 4 to 16 decoder which selects one column in each group. Okay. So, and then so you have basically you select one cell in each column by one decoder, and then you select one column in each group, and then you have another decoder, a third decoder which selects one group, okay, out of the remaining 2 of the 2 to the power 7 groups. So, basically you have a 3 dimensional decoding, that is you have 3 decoders which select for selecting the particular cell. So, one decoder selects one cell in each column, and another decoder selects one column in each of these groups, 2 to the power 7 groups, and another decoder selects one particular group to so that finally you have selected one particular cell. Okay. Now, let us see how this functions. So, this is the circuit of one column. This is how one column is going to look. Okay. So, at the column, so this is again now internally, as we said, it is BiCMOS levels. So, this is negative voltages as in a BiCMOS memory. So, VCC would be actually ground and the negative voltage would be actually minus. Okay. Now, for reading operation, what is done is, while you are reading a particular cell, then these PMOS transistors here, okay, are on. This is on for the reading operation, and these transistors actually form the load for these cells. Okay, this form a low resistance load for these cells. So, while we are reading, what happens is, once we select the cell, these PMOS transistors are on, and since we have a very low resistance load, it creates a differential voltage of around 90 millivolts only on on these two lines. A small differential voltage of 90 millivolts is only created on these lines. Okay, and these bipolar transistors are off during reading operation. So, this 90 millivolts load is differential, has to be sensed. So, what is done is this is Y naught bar. So, if this particular column is to be sensed, this line goes low. So, these PMOS transistors are on, and so this particular difference voltage is available on these two lines. Okay, this 90 millivolt differential voltage when a particular cell is selected. And again here, so basically Y naught to Yn. So, these are in a particular group in a column. These columns form a particular group. So, one of these particular columns is going to be selected, they are all on this line. So, on this line you have the difference voltage corresponding to the column in this particular group which is selected, and this 90 millivolt line voltage is available here. Okay. This part of the circuit is off, I will explain later on. This is basically used for writing operation. Okay, this part of the circuit. So, this 90 millivolt differential voltage is available here, okay, at this point now. Okay. Now, these are nothing but emitter followers, okay, and then this goes to the input of a differential amplifier. So, at the input of this differential amplifier, these two transistors, the input base voltages, they have a difference of only 90 millivolts. But we have already seen while studying ECL gates that the 90 millivolts difference between the base voltages is sufficient to have create a large difference in current, collector currents. Okay. So, what happens is because of this small difference voltage, okay, one of these transistors is going to carry a large current, the other transistor is going to be practically off. Okay. So, there is going to be a large difference in the collector currents of these two transistors. Okay. So, this difference in collector current must be sensed. Now, what happens is this is the sense, this is the basically what we are doing is also we are doing a group decode. So, this output which you have is corresponding to a particular group of columns. So, you have 2 to the power 11 similar groups. Okay. So, you have this is the output say of another group, okay, similar to this. Okay, and all of them are connected, the collectors of all of them are connected to this same pair of lines here. Now, here if you look at this circuit, so this for this particular differential amplifier here you have a NMOS transistor, okay. Only when this NMOS transistor is on can a current flow. Okay. So, what happens is you have 2 to the power 11 such groups here, and another output of the decoder is going to select only one out of this 2 to the power 11 differential amplifiers. So, only one of these 2 to the power 11 differential amplifiers is going to be on. So, although you have a voltage difference at the base emitter at the bases of these two transistors for all these transistors, but only one of these differential amplifiers is going to conduct. So, basically you select one out of the 2 to the power 11 groups. Okay. So, the current flowing, the difference is actually corresponding to one of the 2 to the power 11 groups, and in that group one column, and in that column one particular cell. So, we basically have the difference, the information corresponding to the particular cell we have chosen available on these pair of lines. Now, let us come to this part which is the final sense. So, we have a difference in current, okay, which we have to convert into output voltage. Okay. Now, what happens is if you look at this particular circuit, this is a very interesting circuit. Okay. Now, what happens is there may be a current flowing IC here, okay, which is the collector current of the differential amplifier stage we have already seen. Okay. Now, this is a fixed current I naught. Okay. So, the emitter current of this bipolar transistor here is actually IC plus I naught. Okay. Now, the VBE, the base emitter voltage of this bipolar transistor is actually related to IC plus I naught, to the current flowing. Okay. If the current is small, the base is almost 0, then the base emitter voltage is also going to be very small. But if the current is appreciable, then the base emitter voltage rises. So, what happens is if you look at the output of this differential amplifier stage, okay, between the two lines only one line is going to carry appreciable current, the other line is not going to carry current. Okay. So, if you look at between these two transistors, so what happens is they are identical. So, what is going to happen is in one case the emitter current of this is I naught plus IC, and the other case it is only I naught because IC is almost 0. Okay. So, there is going to be a difference in the base emitter voltages of these two transistors, okay, and that is what it sensed. So, what you have is this VBE, the difference actually. So, this is going to be, this is VCC, say VCC minus VB, and then you have an emitter follower. This is nothing but an emitter follower. This is again fed at the base of this differential amplifier. Okay. So, this what you have is here the base voltage corresponds to depends on the VBE drop of this transistor, and the base voltage here corresponds to the depends on the VBE of this transistor. So, you have a difference in voltage here between the two base voltages, which is then sensed because this is a differential amplifier. Any difference in base voltage will result in a difference in current. This is nothing but a ECL stage, you see. So, you have what you have is again going to be a difference voltage here between the two collectors, which is then again followed up. This is the output buffer basically the next stage. So, you have two this is the emitter followers again, okay, from the previous stage, and then it is fed again to a differential amplifier stage or an ECL stage, as whatever you call it, okay, and the two voltages are here. So, basically here the output from one, now you have just you require one output, single ended output. So, this output is going to be fed here. So, whatever information you have is then available at the output. So, that is how the reading is done. Okay. So, whatever you particularly select one particular cell and that information is passed on to the output. The important point here is that between the two lines, okay, with the help of these NMOS transistors, a low differential voltage, you a low load resistance basically, you create a very small differential voltage between the two lines, only 90 millivolts. So, that it is very fast because although you have a large data line capacitance, the change in voltage is extremely small. So, that makes it very fast. Okay. Now, about the writing operation. While the writing operation is done, what happens is these NMOS PMOS transistors are all off during the writing operation. Okay. Now, what happens is the input for the writing operation is from the data lines. You have data and data bar. Okay. So, if the data is so normally, okay, these would be both high. Now, what is done is one of these lines is going to be pulled down, okay, to write either a 1 or a 0. Okay. Suppose this data line is pulled low, what happens is this goes low. So, this is available here. So, this is Y naught into W, W means write. So, it is AND of the column select and the write. So, this is selected while writing. So, this information is available, the 0 voltage is available on this line. Now, this other line is high. Okay. So, all right. Now, what happens is what is the need of this part of the circuitry? I will just explain. So, if this line goes low, what happens is this PMOS transistor turns on, okay, because the gate voltage turns low, and so this bipolar transistor turns on. So, what happens is there is going to be the other line is VCC high. So, there is going to be a VBE drop across this transistor, and this emitter voltage of this bipolar transistor is going to be nothing but VCC minus VBE. Okay. Now, this voltage is available. Okay. This voltage is now available through this pass transistor on the other line. Okay. So, while you are writing, what happens is what you do is one of the lines is pulled to low, okay, and the other line simultaneously is pulled to VCC minus VBE. So, this is shown here. Okay. I will just draw it, amplify it a little bit. So, while writing, what happens is one of the lines goes low, okay, and the other line is pulled to VCC minus VBE. Okay. So, why is this? We will see that. So, as soon as the write cycle is over, what happens is then this output, this data line goes high, okay, and then this bipolar transistor, okay, this bipolar transistors are turned on. Okay. These two bipolar transistors here would be turned on after the write cycle is over, and these bipolar transistors, this is write bar. So, once the bipolar the write cycle is over, these transistors turn on, and these bipolar transistor helps to pull up the output voltage, okay, pull up the data line, basically data line voltages. So, what happens is this voltage here, okay, which had gone low, is going to be pulled up very fast by the use of these bipolar transistors. Okay. And then what happens is this can only pull up, the bipolar transistor can only pull it up to VCC minus VBE, because once this line goes to VCC minus VBE, then this, and since the base voltage is VCC, then this bipolar transistor can no longer pull it up because it turns off. And then finally, okay, this output voltage, okay, is going to rise slowly, because now after the write cycle these turn on, these PMOS transistors turn on, and then both the line voltages are pulled slowly towards VCC. So, they move like this. Okay. Now, just to explain why one of the lines, so one of the lines is pulled low, the other line is also pulled to VCC minus VB. The reason being is that if this was not pulled to VCC minus VB, the other line remaining like this, okay. Now, this other one line rises sharply to VCC minus VB, okay, this is VCC. Now, there would still be a difference in voltage of VB between the two line voltages. So, if there is a difference in voltage between the two line voltages, we cannot actually make the circuit is not ready for a read operation. Okay. The circuit, for the circuit to be ready for a read operation, the two line voltages must be equalized. Okay, because we remember that when we are reading, we are actually sensing a small 90 millivolt differential voltage. Okay. So, for that, okay, the two line voltages must be equalized very quickly. So, that is why the other line voltage is also pulled down to VCC minus VB. So, once this voltage, okay, on this line goes to VCC minus VB, both the lines are equalized, and then although it is not, both are not equal to VCC, they are rising slowly, but both the lines have equal voltage. So, it is ready for a read operation. Okay. So, it is ready for a read operation at this instant only. So, that is the reason why the other line is going to be pulled down. So, basically what happens is, while writing, we force one line to ground, okay, or should not say ground, actually the lower potential in this circuit, okay, the minus VEE, okay, and the other line to close to VCC. So, this forces the cell, okay, to take up a particular, so basically with that we write into the cell, we write, we turn one of the NMOS transistors on and the other NMOS transistor off in that particular cell, which is selected by the X decoder. So, that is the write operation in the particular, in this particular memory. So, once the write up cycle is over, okay, now the PMOS transistors are on, and this particular transistor is there to help in equalizing the voltages. Okay. So, these PMOS transistors are on and the circuit is ready for a read operation or another write operation. Okay. So, this is how BiCMOS SRAM circuit looks like. So, basically you have these cells, okay, which are 4 transistor cells. So, these are pre-charged to VCC. In this case, of course, VCC is 0 volts and VEE would be minus this 4.8 or whatever. Okay. So, this cell, which is a 4 transistor cell, would, one of the transistors would turn on to reduce the voltage slightly. Okay, because this is a 4 transistor cell, not a 6 transistor cell. So, that creates a small difference voltage, which is basically being sensed. Okay. So, this is how, just to give you a flavor of the type of circuit used in BiCMOS static RAM. So, you have first ECL input, which is converted to BiCMOS levels basically, although the voltage levels are negative. Then with that you select a particular cell. In this case, you have a 3-level decoding, and then the sensing is done by bipolar difference. The small difference voltage is created, only a small difference volt, 90 millivolts, that makes it so fast, and then this 90 millivolts is then fed to the base of a differential amplifier, which creates a difference current, which is then sensed, which this difference current creates a difference in VB of the 2 transistors, which is then finally sensed and again converted to ECL level. Okay. So, this is the circuit of a BiCMOS static RAM, and as I said, the BiCMOS static RAM is going to be much faster than CMOS static RAM because of these properties. Only a small difference voltage on the data lines is necessary, and we are using a bipolar sense amplifier to sense this small voltage. So that brings us to the conclusion on this section in static RAMs. So next class we shall actually take up another form of memory, which is the dynamic RAM.